Okay, so the main point for this chapter isn't just transition metals, but complexes which they form called coordination compounds. And so coordination compounds are what are formed when you have a metal cation. So I'll just represent that generically as an M plus, plus some number of ligands, which I'll represent with an L, and that's going to form MLN. In this case, the metal cation is acting as a Lewis acid, and the ligand is acting as a Lewis base. And so what that means is that the ligand is going to have a lone pair of electrons which it will donate to form a new covalent bond with the Lewis acid or the metal cation. So the new bond that is formed between the metal cation and the ligand, and I'm going to spell ligand just so that you know how it's spelled, ligand. Okay. This is called a coordinate covalent bond. Okay, so coordinate covalent bond, is that on screen? Just barely. Okay. A coordinate covalent bond is a bond where both electrons that form that bond were donated by one of the bonding partners. Most bonds will have one electron shared from the left and one electron shared from the right. It's a very egalitarian relationship. Well, here it's very unequal. The ligand provides both electrons. In the context of coordination chemistry, we can also call these dative bonds, which I might use if only because it's shorter. The ligands could be charged or they could be neutral, which means that the Lewis adduct or the coordination complex or the coordination compound, it could be charged, in which case we would call it a complex ion. If it is charged, we'll call it a complex ion, or it could be neutral, in which case we would call it a coordination compound. And that all depends on the balance of the total charges. Your metal cation will have a certain positive charge. Each of your ligands may have a negative charge or they may not, and then there will be a certain number of them, and you just add all your charges up. Complex ions can be positively charged overall, they can be neutral and we'll call them a coordination compound, or they could be negatively charged overall. When you have a complex ion, so there is an overall charge, well, oftentimes it will attract other ions to sort of neutralize the charge. So we want to distinguish between ligands which are covalently bonded to the metal and other charges which are just counterbalancing that overall charge. So the primary coordination sphere, the primary coordination sphere is the ligands which are actually covalently bonded with the metal cation. And the coordination number is the number of atoms which are forming new bonds with the metal cation. That's not necessarily equivalent to the number of ligands. We'll get into that in a moment. Oftentimes it's the number of ligands, but more precisely it's the number of new atoms which are bonding to the metal cation. So that coordination number will often be 2, 4, or 6. And I suppose there may be some really exotic examples where it's not those three numbers. Sorry, hold on a sec here. Okay, so the atoms which do form covalent bonds are called donor atoms. And donor atoms must have a lone pair of electrons. And they are generally more electronegative. So things like oxygen, nitrogen, sulfur, fluorine, chlorine, there'll be atoms which have a high enough electronegativity that they have a high electron density around them in the context of whatever other covalent bonds they might have. And so they need a lone pair, and they're generally something like nitrogen, oxygen, fluorine, chlorine, sulfur, the more electronegative ones. So in addition to the primary coordination sphere, there will be a secondary coordination sphere. And this includes the ions and molecules which just surround the complex and are attracted to it through intermolecular forces, but not through proper covalent bonds. So here's an example. The cobalt has 6 amine groups attached to it. And so the coordination number in this case would be 6, right? Each of the nitrogens on the ammonia molecules is going to have a lone pair, and that lone pair is going to be used to form a new covalent bond. And you can see that in the diagram. They compose the primary coordination sphere, those 6 NH3 molecules. But because the cobalt has a 2+ charge, that would make the complex ion charged overall. And in solution, charges need to be balanced. You'll never really find a solution that has cations without some anions somewhere to balance out that charge. So in this case, there needs to be anions somewhere, and here they are. These 3 chlorines over here are not bonded to the complex ion, but they will be nearby. They are a part of the solution. If you were to evaporate all of the solvent, then they would form an ionic compound with ionic bonds between the anions and the complex cation. But anyway, they compose the secondary coordination sphere because they are not covalently bonded. You can also have waters as a part of the secondary coordination sphere. Any ion in solution is going to have many layers of water molecules that orient themselves around it. So let's go ahead and erase this. Okay, we've got one more figure. Give me a sec. So ammonia is a very common ligand. So here we have a zinc 2+ cation. It will form a complex with 4 ammonia molecules. And so you can see that the ammonia here have their lone pair, which is going to form a new covalent bond. And the complex in the end is still carrying a positive 2 charge. So this is a complex ion. And the coordination number in this case is 4. There are 4 ligands that there are 4 atoms that are involved in forming new covalent bonds with the zinc. Okay, now some ligands are actually capable of forming more than one covalent bond. So you can have a ligand like an ammonia molecule that can form only one bond. That's called monodentate. Dentate is like teeth in Greek or something, and so it has only one tooth. There's only one way that it can bite that cation and form a bond with it. Other ligands are polydentate. And polydentate molecules or polydentate ligands are able to form 2 or more covalent bonds through multiple donor atoms. And we'll see how that works in a minute. In the end, we've got enough information now to talk about some particular ligands. So an ammonia molecule in the context of coordination chemistry is called an amine ligand. And you'll notice it's monodentate, and the donor atom is the nitrogen. That's where the lone pair is located. Water, or H2O, is actually called aqua in the context of coordination chemistry. It's also monodentate. It's the oxygen that will form the covalent bond. So you can look at all of these. I just want to go down to the carbonate, CO3 2-, the carbonado ligand. It is bidentate. If you were to draw a Lewis structure for the carbonate, you would have a double bond from the carbon to one of the oxygens, and then single bonds to 2 of the others. And each of those oxygens which are single bonded will carry a formal charge of -1. Now resonance would tell us that actually all of the carbon-oxygen bonds are the same, but at any rate, the geometry makes it so that only 2 of the oxygens can be facing the cation at any given time. And carbonado ligand can form covalent bonds between the metal cation and 2 of its oxygens. So carbonyl there is the name of carbon monoxide in the context of coordination chemistry. You see a couple of ones here with big long names. So ethylene diamine, you can see the chemical formula there. It's just a diamine organic molecule, and it is bidentate. So each of the nitrogens there on either end of that ethene backbone is able to form a new covalent bond. And then EDTA, ethylene diamine tetraacetate, is the name of that ion. In the context of coordination chemistry, it's ethylene diamine tetraaceto. That is a hexadentate ligand, and so it's able to actually form 6 covalent bonds, 4 through oxygens and 2 through the nitrogen. We'll see a picture of that one later. Anyway, here are a few more. The oxalate ion becomes oxalato, which sounds like some sort of an Italian dessert item or something. There are a couple more there that are bidentate. Or the nitrito is monodentate, but it could bond either through the nitrogen or the oxygen, but not through both at once. And we'll deal with that actually tomorrow a little bit. So let me skip ahead a little bit. So these polydentate ligands are, it's important to realize that polydentate ligands are a whole lot more stable. We've encountered coordination compounds before in the form of formation reactions. Remember, they got one brief section when we were talking about equilibrium chemistry. And so the Kf value there, that's an equilibrium constant, and the higher the value, the smaller the concentration of remaining reactants and the higher the concentration of products. These are Kf values tend to be large, and so it's like 99% product. But if we compare nickel complexing with pyridine or complexing with bipyridine, well, the bonds would at first seem to be really, really similar. The pyridine and the bipyridine molecules look the same. Bipyridine is basically just two pyridines next to each other. But if we look at their Kf values, then it's a difference of 10 orders of magnitude, which is 10 trillion. Is that right? 3 is 1,000, 6 is million, 9 is billion. So 10 billion. A difference of 10 billion times more stable to have the bidentate ligand. The reason for that is that even though your Kf values are very high and the ligands are very stable, they bond, and for the most part they're going to stay on there. Well, this is a dynamic equilibrium, and so even if the concentration of reactants is very small, the reality is that ligands are, with some regularity, falling off and they reattach. And so instead of thinking of it like the ligands attach and never come off, it's better to think about it as like what percentage of the time do they remain attached, and then what small percentage of the time do they detach themselves. And when you have a monodentate ligand, if it does detach, well, there's the possibility that water molecules will buffet it away, and it may take some time for it to work its way back and reattach. But for a bidentate ligand, if one of the teeth lets go, the other one will still be held on, and so it'll always be held in the same proximity with the cation. It'll be held probably in a configuration where the lone pair of electrons is always really close to the metal cation. And so in order for a bidentate ligand to actually fully detach, both of those covalent bonds need to break simultaneously, which is exceptionally rare. So that's why bidentate ligands here are have such a high Kf value. So we're going to look at one more. Oh, and that's called the chelating effect. What do they call it? The chelate effect. I'm going to write that down for you. Sorry, give me just a second. So polydentate ligands are particularly stable due to the chelate effect. So a polydentate ligand might be called a chelating agent. And chelation would be the act of a polydentate ligand attaching itself to a metal cation. So this is really important in biology. A lot of our proteins are going to essentially be very large ligands which attach themselves to a metal cation. If you think about how hemoglobin is a protein that's all built around an iron cation center, then that's one example. And here we see the Lewis structure for EDTA, that's the ethylene diamine tetraacetate ion. And then we can see how all 6 of its bonding positions are able to form new covalent bonds with the metal cation over here. So EDTA is an exceptionally strong chelating agent. Once think of it like an octopus that's got lots of arms with lots of little suckers. Well, once one arm grabs onto a fish with its sucker, then the octopus is going to pull it right in. It'll grab it with all 8 of its arms, and that fish isn't getting away. So EDTA is like a chemical octopus, where as soon as one of those donor atoms is able to form a covalent bond with the metal cation, well, the other 5 donor atoms are sure to follow, and it's never going to let go. It would require all 6 of the donor atoms to simultaneously break their bonds, and that is not going to happen. And so this makes EDTA very useful. A lot of metal cations are toxic. If they find their way into your body, then they're going to wreak all sorts of havoc. But if they're wrapped up in an EDTA blanket, then most of their toxic activity isn't able to happen. It detoxifies the metal cation. So if you ever do have like heavy metal poisoning, one of the interventions that medical professionals might choose to do is to give you a high dosage of EDTA in the hopes that this molecular octopus is going to grab all those metal cations and just hold on to them and sort of disempower them from doing their toxic chemical reactions. Okay, so one last quick figure. So we've seen a few examples of coordination complexes, and they will adopt geometries that are sort of similar to what we saw with VSEPR theory. Now, there's not going to be any discussion of hybridization or what sorts of bonds are overlapping or all of the different components of VSEPR theory that we saw before. But they follow the same basic premise that your covalent bonds are composed of electrons. Electrons are negatively charged, and so they're all going to be mutually repulsing each other. And so they'll try to adopt these geometries which generally point as far away from each other as they possibly can. So if you have a coordination number of 2, then that's going to be a linear molecule. If you have a coordination of 6, then that's going to be an octahedral molecule. If you have a coordination number of 4, it gets a little bit tricky. So some compounds are going to adopt a square planar. Pardon me. That square planar geometry will tend to be metal cations that have fewer d electrons. And the tetrahedral geometry will be with metal cations that tend to have more d electrons. And I'm not going to expect you to remember that or to draw a hard line, but something like titanium or manganese might form a square planar complex, while something like copper or zinc would form a tetrahedral one. And so these geometries are actually going to come into play tomorrow when we talk about some of the aspects of coordination chemistry. Okay, and that's it for 22.3. 22.4 is about nomenclature. And I've made the decision that nomenclature is just going to go in one ear and out the other. It's all very different than what we're used to. Like everything has a different name, and you know, you're going to get an opportunity to learn about complex chemistry nomenclature when you take inorganic chemistry later on. And so I thought, well, even what I could teach you, you'll forget by then anyway, especially since we're doing this unplanned remote learning and everything is kind of being changed at the last minute. So we're just going to skip section 22.4. It really just is not worth your time. So tomorrow we'll cover the rest of chapter 22 actually, and we'll be well positioned to finish on time with chapter 23.